In our last video, we created this array, which is a series of sound samples at 16,000 samples per second. Each one of these represents one part of the sound, and we want to be able to play these out over a microchip PIC. Since the last video, I've modified this file a little bit with some compiler directives. We're going to be using the XC16 compiler for Microchip. It has a couple of limitations. First, it doesn't allow arrays longer than 32,767. So we took our array and we broke it into two separate parts. And we'll handle this switching between the two arrays in software. Also, since there's not 32 or 64K worth of RAM, we said store this data in the program space. So now let's see, what do we have to do in order to actually play the stuff out of the PIC? Well, we're going to start a new project. This is in Microchip's MPLab X development environment, a new standalone project. We're going to use a 16-bit microcontroller. FJ256GA702. That's the one we're using. Good with all of this. We're going to use the XC16 compiler. And we're going to put it in my Fortnite chest area. And we will call this deck test. Basically, we're testing out to see if we can drive this data out of the digital analog converter, or actually the comparator reference is what we're going to be using. So now we've got an empty file. We're going to go up to Tools, Embedded, and use the Microchip Code Configurator. This tool is really easy to use. It helps you set up the peripherals. You have to still understand what the peripherals do and the various functions. You should be familiar with the data sheet, but this particular tool goes a long way towards making it so that you don't have to set every bit in every register. So for this, we've really only got two things we want to do. We want to enable the comparator voltage reference. So we moved that up there. And we're going to need some way to get the 16 kilohertz clock that we want. So we'll just use a timer. We'll start with the system module, 8 kilohertz. Let's go ahead and use the PLL. That'll get our system clock up to 32 megahertz. The rest, the peripherals will run on the 16 megahertz clock. And that's probably all good. We're not going to use a watchdog, anything like this, because this is just a proof of concept. Let's go into timer 1. And we know that we want a 16,000 hertz signal. 1 over that. Okay, 62.5 microseconds. So we want our calculated period to be timer period. All right, and so it calculates the period count for us, and it turns out that that's a perfect divisor of our 16 megahertz clock, which kind of makes sense, so that should work very good. And we want an interrupt. We'll go ahead and throw our code to update the voltage reference inside of that interrupt. Let's go over to the CVR. This one's pretty simple. Enable CVR output. We want that so that the voltage actually comes outside of the chip. Source selection, value selection, all of this looks good. So let's say generate. That shouldn't have taken long. So we come over here. We get a main file. Not much happening here, just an empty loop. More importantly, we get the timer 1 file. And if we look in here, there is an interrupt handler that's predefined for us. Before we build any code, let's take a look at the actual circuit that we've built, and we will see how that works. Here we can see the circuit that we're going to be using. In the center is the PIC 24FJ256GA702. It needs a pull-up on its reset line. It needs a couple of 100 nanofarad capacitors on its VDD line. There's a VDD here and up here, although they're combined in this symbol. And it needs a 10 microfarad cap on its V cap for the internal voltage regulator. We're going to be hooking up to an ESP01 dev board. We aren't really doing anything with the ESP8266 in this project, but this dev board has a USB on one end and 3.3 volt on the other, so a lot of times I'll just plug it into a breadboard when I need a 3.3 volt power supply. Over here, we have the Lm386 Dev Board, and this is just a board that I got on AliExpress. It has the Lm386 audio, I don't want to say op amp, but audio amplifier. There, it's got screw-down terminals for a speaker, and it's got a pot in place so that we can control the gain. The speaker we're going to be hooking up to is another special I got on AliExpress. Got a few of these, and they're nice speakers. They're real thin, which makes them good for putting in things. They don't sound super, but they're good enough for our purpose. For the schematic, we are not showing the speaker over here. It is just connected on that side. If we were going to make a PCB that connected to this, the fact that there's a speaker over here wouldn't show up on the schematic, so I'm not going to show it. Here you can see all this. We have a variety of extra wires here. The reason for this is that I am connected up to an MPLab PIC Kit 4 that's going to let me program the thing. I've also got a couple of leftover LEDs and resistors from a prior project where I was working on some I2C stuff. Up here you can see the Lm386 Dev Board. If we end up using this in the final design, I'll cut the traces to that LED. We don't need that LED burning a lot of extra power. I'll likely desolder this header and solder the wires from the speaker directly into the board. So let's do a quick check and see if we think that our interrupt frequency is correct. Okay, so we will hit go. We hit our breakpoint. Let's add a watch window on this. And we can see that the value is currently 0. Let's take this breakpoint out and we'll run for about 10 seconds. 1, 1000, 2, 1000, 3, 1000, 4, 1005, 1006, 1007, 1008, 1010, 1000. And we see, okay, we got 173,000 across more or less 10 seconds. We also are running on the internal oscillator, which is plus or minus 1 or 2%. I don't remember which, so that could throw us off a little bit, but we're definitely in the proper ballpark here. As they say on the cooking shows, I actually prepared one of these earlier. Essentially what we're doing is we're saying, okay, we're going to be a little bit sloppy here and just throw the externs in. This code is going to be throwaway after the next 5 minutes anyway. We're going to create a sample counter. This array counter is left over. We don't actually need that. We'll save this here. Come in here. MPLab should say, oh yeah, you see that this has changed. And here it is. So essentially, we saw before, and we need to include that array that we had prior. We saw before that we had to break that array into 2 separate steps. Again, we put 32,000 bytes in the first array, 32,767 in the second array. So you can see, basically, as we run through our samples, we do one or the other. Then when we get essentially what we're doing here is we are taking the controller, the bottom 5 bits of this guy are the output, and so we're going to take the top 5 bits, rotate them to the right 3, OR them, and these 2 bits continue to leave the voltage reference on and also drive it to the outside pin. So we're going to get a value that goes in there that should generate an analog voltage. Finally, after we do that, I've got just a relatively long delay in here, so it'll wait a little while and play the next sample after that. This is essentially always running in a loop. 16,000 interrupts per second is a bit much. One of the things that we could look at here, maybe you can hear that running in the background. One of the things we could look at here, this chip has DMA. The DMA is not capable of directly accessing the flash memory, only the RAM. However, it is possible for us to map some of the flash memory into RAM space in the extended data space and then access that with the DMA. However, that seems like an awful lot of trouble. 16,000 interrupts is a lot, but not a horrible amount, especially when you've got such a little amount of code into it. And this microcontroller basically is going to be doing nothing else, but also driving some SPI traffic to drive our LEDs at the same time. That SPI traffic, I do anticipate that we'll use the DMA to feed the SPI with. So I'm going to go with this for right now. If it turns out we need to go a more complex route, map the flash into the shared data space and then point the DMA at that, we can set that up later, but I don't think we're going to need that. I'll hold my mic over it and you can determine for yourself what it sounds like. Just for curiosity's sake, let's go back and play the original WAV file. I would definitely say that qualifies as a success. Broadwell Consulting provides help developing medical devices with a focus on developing embedded firmware, which is compliant with EN 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting.